Alright everybody, in this video we're going to go through the notes chapter 12.1 and 12.2. Right, the notes combine them into one chunk. And so what we're talking about is this idea of correlation. Okay, so some of the things we hope to accomplish is be able to create and interpret a scatter plot, be able to describe scatter plots and correlation, and use technology to calculate the correlation coefficient between two variables, and build intuition of a correlation coefficient and scatter plots. Okay. Let's talk about scatter plots first. Scatter plots are a way to visualize our data, okay, to basically take data in a table form and get some sort of a graph out of them. Okay, and once we get that graph and we have that visual plot of our data, we want to then be able to analyze it. And we're going to see that one of the ways we do that is by creating what we call a regression equation. Basically an equation that sort of estimates as best it can all the data, or the formula for all the data. Okay, so that's what we're going to get into. Not in this video, but in the next one. Let's just first make sure we're okay with the idea of a scatter plot. All right. So a scatter plot is literally a scattering of data points, like I said. And so let's plot those now. So here they are asking us, is there a relationship between the amount of fat in a McDonald's sandwich and the total calories it contains? So they've given us a whole bunch of McDonald's sandwiches here. They've given us the amount of grams, or how many grams of fat are in the sandwich and how many calories are in the sandwich. And we want to see if there's a link between these two variables, right? Between the amount of fat in a sandwich compared to its calories. When you just look at the raw data, it's hard to see whether or not there's a link between them. Our eyes just can't throw that together. And so you generally, from a table, it's tough to determine if there's a relationship or not. But once we kind of visualize it and put it on a graph, look at the scatter plot, it becomes very apparent whether or not there is a relationship between the two. Now in general, when you're doing these, it doesn't matter which variable goes on the x-axis or on the y-axis. Okay, generally one might seem more obvious choice than the other. Whichever one goes on the x-axis, that's what you might hear referred to as your input. It's sort of the one doing the driving. In other words, what I want to kind of determine is, if I have this many grams of fat, how many calories can I expect to have? If I have this many grams of fat, how many calories can I expect to have? Okay, so like I said, you can do this both ways. It doesn't matter one bit. Just try and think about, does one variable make more sense? And in this case, I don't think it matters either way. I mean, at least to me, one doesn't make more sense than the other. But they've gone ahead and provided this table for us. So we're going to put the grams of fat on the horizontal axes and the calories on the vertical axes. And we're going to graph each one of these. So I'll do one or two, and then maybe I'll pause it real quick and do the rest. So just taking a look at the first one, a hamburger. 9 grams of fat, 260 calories. So on the graph, find 9 grams of fat, 5, 6, 7, 8, 9, and then go up to 260 calories. Now notice the distance here. It looks like they're counting by 20s, right? Like 20, 40, 60. Nope, they're not. They're counting by 25s. 25, 50, 75, 100. 125, 150, 175, 200. So each of these vertical marks here is 25 points. So let's see, we got to get as close as we can to 260. So 9, and then go up to, there's 200. That would be 250, so a little bit above it. And sometimes you're just going to have to eyeball or guess it, and that's okay. The idea is just to help us visualize if there's a relationship, not to accurately put these down, or so accurate that we drive ourselves mad. So let's look at the cheeseburger. 13 grams of fat, 320 calories. So find 13 grams of fat, 11, 12, 13. Go up to 320. There's 300. And the first line above it would be 325. So it's a little short of that. I'll do one more and then pause it. So let's look at the quarter pounder. 21 grams of fat, 420 calories. So find 21 grams of fat and go up to 420 calories, about there. Okay, So hopefully you get the idea. I'm going to pause it and just fill in the rest real quick so we don't I don't waste your time here. Okay, so I added all but the last one. Let's throw the last one on there together. Make sure you got the idea. Find 5 grams of fat and then draw up to 300 calories. So 5 grams of fat, 300 calories. All right. So if you look at the scatter plot, whereas the table doesn't necessarily help me visualize whether or not there's a relationship between the two, the scatter plot really, to me, shows a strong relationship. In other words, there's almost like an equation that can be used to make predictions about as you increase the number of grams of fat, how much the number of calories will go up. And this is the whole idea of this chapter, is essentially coming up with this line and making sure that it's valid and legit and the best one we can get. Okay, that's kind of the goal here. And so let's answer a couple of these questions. It says, what happens to the number of calories as the number of grams of fat increases? Well, we just kind of said it, that as the grams of fat increased, we saw the number of calories go up as well, right? That seems to be the trend we're seeing here. So as grams of fat increases, the calories are increasing as well. Okay. Well, here's the thing. Why we want to learn how to describe this line. Because if I can get the equation of that line, I'm then looking at a formula. You know, I've got some sort of formula here that that I can use to predict this data, okay? And so that's where we're getting to this, because then I can use that formula to sort of make estimates on other questions that we maybe don't have data for. So here it says, if McDonald's introduced another sandwich that had 19 grams of fat, estimate how many calories you would expect the sandwich to have. If I were to find 19 grams of fat, that's right here, I'm just going to draw up to this imaginary line I drew. I mean, to me, that would be around where we would expect the number of calories to be. So the line I drew just randomly happened to cross right at 400. I think it's got to be around 400 calories, give or take some for sure, but it would be close. So I would expect 19 grams of fat to correspond to, 400 calories. All right. So we can do more analysis if we actually know the equation of that line that tries to best estimate all the data. And again, that's where we're getting to with this. So on the next page, got some new terminology here. It says that when two variables are associated, okay, then there is some relationship that exists between them. So for example, males are associated with shorter hair and females are associated with longer hair. So association just means that in general, there's a link between them, or the data would often show a relationship exists between the two. Now, we're going to start looking at correlation, okay? And many of the things we're going to analyze would be associations, but if you want to use the word correlation, what we're doing is we're talking about quantitative variables, okay? In other words, they have to be able to be described numerically, both of them, if we want to talk about the correlation. Correlation is basically a measurement of how well two things are associated, okay? I couldn't use the word correlation up here because here I'm talking males and females. That's not a quantitative variable, right? You could talk about the hair length being quantitative because you can measure it, but males and females is categorical. So we could talk about an association going on or a relationship going on, but we wouldn't use the word correlation, okay? Because correlation, we're talking about quantitative variables that I can basically describe and analyze numerically. So here are some associations in which we can refer to their correlation. All right, so example, a shoe size is associated with foot length. So those are the two things you're comparing, shoe size and foot length. Well, those would be quantitative, right? They're both numerical. Here's the idea: as the length of a person's foot increases, their shoe size increases. So if you were to imagine sort of what a scatter plot would look like, maybe down here you have foot length and then shoe size. As a person's foot length increases, we would expect the shoe size to increase as well. So we would probably see data values like this. If I were to just get a bunch of data values of people's foot length and shoe size, we would probably see an uphill trend and probably a straight line, a linear uphill trend. Because that line is going uphill, right, or just up, we would say that that is a positive correlation. Those two variables have a positive correlation. So by describing the correlation, we are describing the direction, okay, in which the association or the relation seems to be going, uphill or downhill. And we're also going to see a way to numerically describe this even better, which is going to help us determine how good of a job that line does at actually predicting those data values. So another example would be the average number of minutes exercised per day is associated with resting heart rate. Again, those are two quantitative or numerical variables, right? Average number of minutes exercised and your resting heart rate. And so it's safe to use the word correlation, or we could talk about measuring the correlation between them, okay? Using correlation to describe the association. So just to get a visual on this, the more hours a person exercises, the lower their heart rate. So I'm going to put hours exercise and then heart rate, or their resting heart rate, okay? And so as the number of hours you regularly exercise increases, people's resting heart rate goes down. Right, their heart is stronger, it doesn't work as hard under normal conditions. So I would expect data values to kind of be doing some sort of this trend. All right, if I were to just have a table of data that gave me the hours they exercise and their resting heart rate, we would expect to see that those that exercise more have a lower resting heart rate. Okay, and so this thing would be going downhill. So you may have guessed it. If they're asking what type of correlation that is, we would say this is a negative correlation. It's really talking about the slope of the line. Positive correlation has positive slope, negative correlation has negative slope, okay, or the line would have negative slope. So in this section, in 12.1 and 12.2, we're mainly talking about making the scatter plot and getting our heads wrapped around this idea of correlation and how we can use certain terms to describe the relationship here. So here's another example, and here they don't give me a table of data, they just give me the scatter plot, all right, so the sort of the visual of all the data. And it says compare latitude with mean January temperature of various cities in the US. What does each dot on the scatter plot represent? So let's look at the scale here. On the vertical axis, they've got the temperatures in January, the mean January temperature. And on the x-axis, we're looking at latitude. All right, so if you remember latitude, looking at the Earth, the equator is at 0, right? And then as you go up towards the poles, you're increasing in latitude, right? You're increasing in latitude as you go up towards the poles. And so I think it kind of makes sense to us that if you go higher in latitude, right, closer and closer to the poles, right, you're getting colder in January. And so that's exactly what we're seeing in here. As the latitudes are increasing, right? As the latitudes are going up, that means you're creeping your way closer and closer to the poles. That's making the temperatures go down. And so that's what we're seeing in these data points. And what each of these single data points represents is this is a random city in the US. This is their latitude on the globe, on planet Earth, and this is their average January temperature. Okay, so that's what each data point represents. So let's say these are actual, let's do latitude, January temp, data values. Remember, when writing things in an ordered pair fashion, we always put what's on the x-axis first, and then the y-axis next. These go by many names. They don't go by x-axis and y-axis. In fact, I don't like that. We would call them inputs and outputs, and dependent variables and independent variables, and there's a whole laundry list of terms that these can go by, but I just want to remind us the first one we see on the x-axis, and then this guy, second variable, we read off the y-axis. Okay, so to me it looks like there is some sort of linear equation that could maybe be used to estimate the majority of this data. And notice some of the data is above that imaginary line, some of it's below. The line itself only goes through a couple data points. The process we're going to learn about later, finding the equation of this line, what it attempts to do is it attempts to get a line that is as close to as many people as it can, or as close to everyone, right? So it basically looks at the distance from every data point to the line, right? Every data point, some are really close, some are a little farther than others, and there's a little mathematical process to basically minimize these lengths for everybody, to try and position this line in the right place so that it makes all of these black line distances as small as possible for every data point. Let's see. What direction are the points going? Is this positive or negative correlation? Well, it's going downhill, right? It's going downhill. All right, so we're looking at negative correlation, okay? We could say that as latitude increases, mean January temp decreases. All right. So the last page just helps define a little, how can we describe this a little bit better, this relationship? Okay, so if you're trying to describe an association, you can always describe it by discussing the three following features of a scatter plot: the strength you see, the direction, and the shape. Okay, so when we're talking strength, we want to use words like it's strongly associated, moderate association, or weak association, things like that. Okay. The direction, well, that means uphill or downhill, so positive or negative association or correlation. And then the shape, sometimes all the scatter plots I've drawn so far have looked like a line, but they don't have to look like a line. So the shape would be either linear or nonlinear. And if it's nonlinear, maybe you recognize the shape and you say, oh, that looks quadratic, or that looks exponential, or whatever. So if you happen to know what the shape looks like, from a previous math class, it would be better to be more specific about it. So what they've done now is they've provided us 6 or 7 scatter plots, and they want us to use these descriptors to describe what we're seeing. Okay, to basically describe the scenario here. All right. So let's take a look at this data, this association. To me, there is an association because mainly what I look for is, can you tell the direction it's moving? And to me, it looks like it's moving uphill. In other words, as one variable increases, it causes another variable to change. In this case, increasing. Now, it doesn't look as nice and strong as this one, right? This second one looks like a much better or stronger association. So to me, there's an association going on. It's positive because it's going uphill. And if I had to guess a shape, to me it's linear. I mean, it's not that shape, which would be exponential. It's not quadratic. To me, it mostly looks like a line. So I would say that this is either weak or moderate. Your choice. Positive, linear association. Right? I talked about the strength, I talked about the direction, and I talked about the shape. Okay. Now, this is really it's really subjective. Maybe you would have said, well, that's not weak, I'd call it moderate, or that's not moderate. So it doesn't matter. This is just an example for us to kind of get used to knowing when it would be appropriate to use certain terms. So take a look at this guy. If we called this one weak or moderate, to me this is strong. The data is really tightly centered around that line. It's positive, and again, I just said it's a line. Of all the shapes, to me it looks most like a line. So I would call this strong, positive, linear association. All right. We talked about the strength, the direction, the shape. Now, this third one is a tough one. My eyes almost want me to see a line going like this, but then my eyes almost also want me to see a line going down. In short, to me, there isn't an indicator that when one variable increases, it causes the output or the dependent variable to go up or down. I don't really see that. Like here, it's obvious. When the x value increases, the y value is increasing. And even here it was kind of obvious. X increases, that's pushing the y values uphill. I don't see that here necessarily. And I don't see it going downhill either. Maybe. It's just really hard to tell. In other words, in my mind, this is no association. I would say that there's no association here. And I mean, if I were to run the numbers, it may turn out that I'm wrong, but compared to these other two, to me there's not much of an association going on. So let's take a look at these ones. Now this one, to me, looks like I could fit a line through there. Looks like it's got a little curve, but I think that's just some of the data points. It looks more linear than anything else to me. I would say it's pretty strong. It's pretty tightly packed around the line. So I would call this strong for my strength. The direction is negative. The shape, I would call it linear. Association. Describe the strength, the direction, and the shape if you can. All right, let's take a look at this next one. Now, this one looks positive to me because as one variable increases, as the variable on the horizontal axis increases, it's causing the guys on the vertical axis to go uphill. So to me, this is positive. I would not call this a line, because to me it's not a line as much as it is something exponentially growing. Right? It looks way more like it fits an exponential growth model, perhaps. So I would call this, and strong, I would say it's pretty strong. Yeah, moderate or strong. The data values look pretty consistent. So I would say moderate or strong, you choose. It's definitely positive because I'm going uphill. To me, it's not a line, so I would say nonlinear. I would probably say exponential, because to me it looks like it's exponentially growing, but if you just said nonlinear, that's totally fine. Basically classify it as a line or not a line. Association. So I've got the strength described, the direction, and the shape. Okay, two more here. Let's talk about this one. Let's see. Well, this is incredibly strong. It's not linear. It definitely doesn't make a line. This looks quadratic, right? If you remember from algebra, quadratic is the shape of gives us the shape of a parabola. That totally looks like a parabola to me, and it looks really close to it. So I would say it's very strong. Okay, association. I can't say positive or negative, right? Because in this case, it's a little bit of both, right? As this variable increases, at first it makes the data values go down, and then it makes my data values go up. So I can't say positive or negative. I think it's quadratic, so I'm just going to first by saying nonlinear, basically saying it's not a line, and then I would further say it's quadratic. Okay, so again, I got my strength and my shape. I can't really talk about the direction in this case because it's got them both. Last one. This guy's a little weird, but if you think about what's going on, the question is always, as one variable increases, is the other one going up or is the other one going down? That would imply a relationship between them or an association between them. I don't see any of that here, right? As one variable increases, whatever this is on the x-axis is getting larger, it's having no impact on the heights of these data values. So to me, this would be no association. And we'll see that later, that when you find the equation for this line of best fit, if that turns out to have zero slope, which this one does because it's horizontal, that implies no association. Okay, so the last little bit on here is that daunting looking formula, but don't fear, we're not going to calculate these by hand. They're just showing us the formula. We would do this all on a computer program or StatCrunch or something. But what you're looking at is called the correlation coefficient, R. It's the correlation coefficient. And what that does is that gives us a numerical way to basically gauge how strong a correlation is. Okay, the strength of the correlation and the direction of the correlation. So it's a mathematical calculation that can basically help us answer these questions a little better. Because right here, you know, we're going on sort of what's your opinion on it? Is it weak or is it moderate? You take your best shot. Is it moderate or is it strong? What would you like to say? So it's a little willy-nilly. The correlation coefficient gives us a mathematical number that essentially tells us how strong or weak that correlation is. Okay, so here's how it's calculated. It is the sum of these products. It takes the z-score for each data value x and for each, it takes the z-score for every x value of every data value and for every y value of every data value, adds them all up and divides by n minus 1. Now, let me just show you real quick what these are. This z sub x, I'm going to write z sub x sub I. And don't get confused by this, but basically, if you have a table of data, right, you've got a bunch of x values and y values. So, just making some things up, okay? I've got a bunch of x values here. So for every single one of these, I can find this little z sub x score. And what it is if you were to take all of your data values, you would be able to find an average of all those x values and a standard deviation of all those x values. right? I mean, I could just take all of those data values, plug them into StatCrunch, and it'll tell us really quick what's the average of that short list and what's the standard deviation of that short list. Okay, well, one of these z sub x values is found by taking your observed data value, like so 4, for example, what you observe, minus what the average of all the x's are, divided by the standard deviation of all those x's. And so I would need to calculate one of these scores for every single data value. Right? Again, it's not hard to do, it's just a royal pain in the butt to do. Okay, and it's no more challenging than adding, subtracting, multiplying, and dividing. That's as tough as it gets. It's just a whole lot of it. And so for every single one of these x values, I could find this z sub x score or value. All right, by taking the data value itself minus the average of the group over the standard deviation of the group. And you would do the same thing for the y's. And you would get all of those corresponding y values. And then I would multiply them, and I would add them all up and divide by n minus 1. That's how I would get r. So again, we're not going to do it by hand. The calculator or computer will do it for us. But a couple things. R will always be in between -1 and 1. Okay, it's always going to be between -1 and 1. And it turns out the closer it is to either 1 or -1, the stronger the relationship is. Okay? And the sign indicates whether or not it's a positive or a negative correlation. So if R is positive, then we have a positive correlation. If R is negative, we have a negative correlation. Let me just maybe write that down. R is positive. We have a positive correlation. Or association, and I tend to use those words interchangeably. Remember, if you're talking about quantitative variables, numerical variables, we can use the term correlation. And again, we kind of make a distinction because when you're talking numerical variables, we get these other added goodies because we can analyze those numbers. So this was the correlation coefficient. How strong is the correlation? I mentioned this a little earlier that if you have, well, actually I mentioned slope, but if R comes out to be 0, then it turns out you have no association or there's no correlation between the two variables whatsoever. Some of the nice things about this are scaling or units do not affect R because basically we're standardizing our values here, sort of bringing everybody down to the same level. Doesn't matter which variable is assigned to the horizontal axes or the vertical axes. Now, this is only good if we're using it on linear associations with no outliers. All right, so we wouldn't use this on this quadratic association or something that looks exponential. And we wouldn't want to trust this number if we had outliers involved, okay, because the outliers would radically change these values here. Okay, was that it for this? Yeah, so that's it. So let me just kind of jump back here. What I would know, let me just give an R value for this and an R value for this, a correlation coefficient. And I'm making them up, but I'm basing them off of what we just learned and roughly what they would be. So these are totally just made up. These are both positive, we said. They're both going uphill. So when I calculate the correlation coefficient, I'm going to get a positive number here. Okay, again, it could be between -1 to 1. And because it's positive, I know that it's going to be on this side. Okay, this correlation coefficient number. Now, it's we said weak to moderate, which means that it wouldn't be that close to 1, because the closer you are to 1, the stronger you are. So maybe this correlation coefficient, I have no idea, I'm just making something up, but let's say it's 0.35. It's positive, but it's not all the way to 1 because it's not that strong. well then this correlation coefficient is also positive because it's going uphill, but it would have to be much stronger than this guy. It looks like a much better fit. And so maybe this would be like 0.75, something much closer to 1. Okay. This guy over here, if I wanted to imagine what the correlation coefficient would be, well, it's going downhill. It's a negative association or correlation, so it's definitely a negative number. And we said it's pretty strong, so it would be fairly close to -1, maybe like negative 0.7 or something like that. Again, I'm just making these up. If you had the data values, you could figure out that number exactly. Ideally with the computer, because to do this by hand would be very tedious. All right, that's it for 12.1 and 12.2. In 12.3, we look at how to actually find the equation here of this line that we can use to estimate data, and we'll get to that next. Take care.